In mathematics, a unit vector in a normed vector space is a vector whose length is 1. A unit vector is often denoted by a lowercase letter with a hat, like so. The normalized vector or versor of a non-zero vector U is the unit vector codirectional with U, that is, where U is the norm of U. The term normalized vector is sometimes used as a synonym for unit vector. The elements of a basis are usually chosen to be unit vectors. Every vector in the space may be written as a linear combination of unit vectors. The most commonly encountered bases are Cartesian, polar, and spherical coordinates. Each uses different unit vectors according to the symmetry of the coordinate system. Since these systems are encountered in so many different contexts, it is not uncommon to encounter different naming conventions than those used here. By definition, in Euclidean space the dot product of two unit vectors is simply the cosine of the angle between them. In three-dimensional Euclidean space, the cross product of two orthogonal unit vectors is another unit vector, orthogonal to both of them. Orthogonal coordinates, Cartesian coordinates. Unit vectors may be used to represent the axes of a Cartesian coordinate system. For instance, the unit vectors codirectional with the x, y, and z axes of a three-dimensional Cartesian coordinate system are. They are sometimes referred to as the versors of the coordinate system, and they form a set of mutually orthogonal unit vectors which, in the context of linear algebra, is typically referred to as a standard basis. They are often denoted using normal vector notation rather than standard unit vector notation. In most contexts it can be assumed that I, j, and k are versors of a 3D Cartesian coordinate system. The notations, or, with or without hat, are also used, particularly in contexts where I, j, k might lead to confusion with another quantity. When a unit vector in space is expressed, with Cartesian notation, as a linear combination of I, j, k, its three scalar components can be referred to as direction cosines. The value of each component is equal to the cosine of the angle formed by the unit vector with the respective basis vector. This is one of the methods used to describe the orientation of a straight line, segment of straight line, oriented axis, or segment of oriented axis. Cylindrical coordinates, the three orthogonal unit vectors appropriate to cylindrical symmetry are, representing the direction along which the distance of a point from the axis of symmetry is measured. Representing the direction of the motion that would be observed if the point were rotating counterclockwise about the symmetry axis. Representing the direction of the symmetry axis. They are related to the Cartesian basis, by, equals. It is important to note that and are functions of, and are not constant in direction. When differentiating or integrating in cylindrical coordinates, these unit vectors themselves must also be operated on. For a more complete description, see Jacobian matrix. The derivatives with respect to r. Spherical coordinates, the unit vectors appropriate to spherical symmetry are, the direction in which the radial distance from the origin increases. The direction in which the angle in the xy plane counterclockwise from the positive x-axis is increasing. And, the direction in which the angle from the positive z-axis is increasing. To minimize degeneracy, the polar angle is usually taken. It is especially important to note the context of any ordered triplet written in spherical coordinates, as the roles of and are often reversed. Here, the American physics convention is used. This leaves the azimuthal angle defined the same as in cylindrical coordinates. The Cartesian relations are: the spherical unit vectors depend on both and hence there are 5 possible non-zero derivatives. For a more complete description, see Jacobian matrix and determinant. The non-zero derivatives are: general unit vectors. Common general themes of unit vectors occur throughout physics and geometry. Curvilinear coordinates. In general, a coordinate system may be uniquely specified using a number of linearly independent unit vectors equal to the degrees of freedom of the space. For ordinary 3 space, these vectors may be denoted. It is nearly always convenient to define the system to be orthonormal and right-handed. where IH is the Kronecker delta and is the Levi-Civita symbol. See also, Cartesian coordinate system, curvilinear coordinates, for velocity, Jacobian matrix and determinant, polar coordinate system, right versor, unit interval, unit square, cube, circle, and sphere. References: GBARFKEN and H.J. Weber. Mathematical Methods for Physicists. Academic Press. ISBN A0-12-059825-6. Spiegel, Maria Schorm's Outlines, Mathematical Handbook of Formulas and Tables. McGraw-Hill. ISBN A0-07-038203-4. Griffiths, David J. Introduction to Electrodynamics. Prentice Hall. ISBN A0-13-800 5326-XA.